Hey guys, welcome back to another tutorial on MATLAB, and in today's tutorial I'll be showing you how to solve plane truss problems using MATLAB and a little bit of coding. So I have one problem over here which is a plane truss with 3 elements. So as you can see, we have 3 nodes, 1, 2 and 3, and some forces are applied on node 3, and we are going to find the global stiffness matrix, horizontal displacement at node 2, 3, and reaction at node 1 and 2, and then stress in each element. So let's start with the problem. What can we do is, let's start from your script. First of all, clear all, so it will make the script clear. Now let's type the given over here. So E is 210, GPA is simply E6, and then area is 1, so you can type 1E minus 4, 1E minus 4. So I'm quickly going to run this thing. Let's run this. So just name it example 5.1, save. So as you can see, I'm getting the results. Now let's start with node. So for node, as you can see, we have 3 nodes, and the we consider the origin at this point at node 1, so this node will be 0 and 0. So if we follow this pattern, then for second node we will be having in x direction 2 plus 2, that is 4, and y is 0 because it is on the origin plane. Similarly, for the third node, we have the x as 2 and y as 3. So we have the nodes. Next, we are going to define element connectivity. So element connectivity is basically shows which element is connected to which node. So if I consider first element as this one, that is between 1 and 2, and second in between 1 and 3, and third in between 2 and 3. So for if we consider this as a situation, so first element is connected to 1 and second node, and E and A as well. So E and A will be common for everyone. So this is my first element. Second element is connected to 1 and 3. You can take any, like you can choose your own element numbering. I have chosen, it's like 1 for this one, 2 and then 3. So second element for me is 1 and 3, E and A, and the last one is 2, 3, E, A. So you are getting element connectivity. Next, I'm going to define the displacement boundary conditions. So U, B, C. This is the displacement boundary conditions. So what it says is, we have for first node, we have a fixed thing over here. So its displacement is going to be 0 in x direction as well as in y direction, because it is not allowed to move in any way, because it is fixed. So UBC is the displacement for each and every node. So for first node, x displacement is 0. Similarly, for first node, y displacement is 0. So this first is the indication of node. This is for x direction, and this is the amount of displacement. So we know for first node it is fixed, so x direction is 0. Similarly, for y direction it is 0. So using this thing we can type as for second node. In second node we have a roller support. So roller support, what it does is it will have some displacement in x direction, but it is not allowed to give displacement in y direction. So we have 2 2 0. Oops. So we have defined our boundary condition for displacement. Now let's define the boundary condition for force. So we have the first is fixed, so there won't be any force in this one. We have a roller support at second node, so it will give some amount of force, displacement and something on the x direction. So 2 1 0, because the force is not specified, so we can simply type 0. And at node 3 we have two force components, one in x direction and one in y direction. So the right hand side means positive and left hand side means negative. Similarly, downward means negative, upwards means positive. So using this form we can say 3 1 for x, which is 5, and 3 2 for y, which is minus of 10. So we are done with our force boundary conditions. Next we are going to define the number node, which is size, element connectivity, size node comma 1, node comma 1. So what this number node says is it gives the total number of nodes we have in our problem. So how it defines is it takes the size of all the nodes. So for first node we have 1 2 and 3, so we are getting the number of nodes. Next we have number element. So number element is related to element connectivity. What it will give is number of elements. So we have 3 elements and 3 nodes. Next, what will be our global stiffness matrix, which will be of size 2 times of number node. So we are going to have a global stiffness matrix which is of the size 6 by 6. Similarly, we are going to have reaction forces. So for that, same thing, but this one is only in, and same for displacement. Number 1 now comma 1 now we have defined all our given as well as number nodes and element connectivity. Let's begin with the coding. So for element equals 1 to number of element, we can define n1 equals element connectivity element comma 1. I'm going to simply copy paste few things. Okay, n1 n2 is defined. Let's define x1. X1 will be node n1 comma 1. Y1 will be node n1 comma 2. Similarly, x2 will be node n2 comma 1 and y2 will be node n2 comma 2. So then we will have some angle over here, theta, as a tan 2. This is a general formula. You can use it in number of problems. You don't need to worry with the change. So it will be the same in almost each and every problem, which is similar to plane truss. Next we are going to have some length of each element, which is square root of x2 minus x1 whole square plus y2 minus y1 whole square. Right, so we will have cos theta as well as sine theta. So next we'll have k element, which is EA upon L. This is a general formula for k element. EA upon L cross C square CS. Just a second. C square CS minus C square minus CS. Then we have C cross S square minus CS minus S square. Then we have minus C square minus CS C square CS minus C. So guys, this one is like a general formula for k element. You can find it in any finite element book. I'm just using that formula, nothing difficult. So we have our k element done. Now what we are going to define is K1 for the global stiffness matrix, which is 2 times n minus 1, and K2 is 2 times n1. Similarly, K3 is 2 times n2 minus 1, then K4 is 2 times n2. So then we will have global stiffness matrix Kg for K1 to K2, comma K1 to K2, which is equals to the same. So I'm just going to copy it, plus k element 1 to 2, 1 to 2. So let's make this big. Okay, 1 to 2 is missing. So let's copy paste this 4 times. So first time we have 1 to 2, 1 to 2, then we have 1 to 2, 1 to 2, 3 to 4. And then we have 3 to 4, 3 to 4, 3 to 4, 3 to 4, okay, 3 to 4, 3 to 4. So let's type in end. So we have our global stiffness matrix for So what this code is doing basically is, I'm going to tell you in a very short description about this one. So okay, so what this code is doing is it taking the element from 1 to 3, with each element calculating its n1 n2, node 1 and node 2, and then x1 y1 x2 y2, theta, similarly L, cos theta, and then sin theta, and it's contributing all these values in k element, and then it's substituting that values of k element in the global stiffness matrix. So for each element, that is 1, 2 and 3, so it's going to do it for 3 times. So as you can see, for first time n1 1, 2, similarly theta will be 0. Okay, so after doing it for 3 times, we are going to get the global stiffness matrix. So let's proceed further and find the horizontal displacement at node 2 and 3 and vertical displacement at node 3. So we know that, because we have k, we know that the horizontal displacement at node 2 means this one, this element. So this one is like the displacement at each node. So for first element, node 1, it will have x direction and y direction. For node 2, x and y. For node 3, x and y. So we need to find the horizontal, means third from here, and horizontal and vertical in third node means 5th and 6th. So I'm going to use these and find the displacement. So let's take the k from here so that we can, so we know, so we have 3, 3 and k global matrix 3, 5 to 6. So what we are taking is, as I told you, third element and third row from global stiffness matrix, and then third row, 5th and 5th to 6th column. So I'll tell you, no issues. So third 3, 3 means this one, and then 3, 5 to 6, which means these one point and this point. So we are taking this element, and this element, because we are finding the displacement at node 2 horizontal and node 3 horizontal and vertical. So then after this, we'll have 5 to 6, 3. And AG 5 to 6, 5 to 6. Perfect. So let's do this. So as you can see, what I'm doing here is, so we are finding the horizontal displacement at node 2 and 3 and vertical displacement at node 3. So we are taking the elements from global stiffness matrix. So for that we have defined 3, 3, which is this one, which comes here, and then third row, 5th to 6th column. So this is the third row, 5th to 6th column, which is this one, and this one is coming here and here, right? Next we have 5th fifth to sixth row, third column, fifth to sixth row, third column, which is this one, and then fifth to sixth row, fifth to sixth column. So fifth to sixth row is these two, and column means these four. So these four come over here. This one and this one goes here. So we found the elements. So let's go and find the displacement. So let's define F equals, so for node 2 we have 0, right? Let's say let's see, for node 2 we have 0, for node 3 5 and minus 10. So 0, okay, oops, 0, 5, minus 10, right? So we need to find U, which is displacement, so K upon F. So this is the displacement at node 2 horizontal, and node 3 horizontal, and node 3 vertical. Now let's go and find the reaction at node 1 and 2. So we need to find the reaction at node 1 and 2. So for that we'll define our global displacements, which we know earlier that we have 0 at node 1, so 0, 0. Then for node 2 horizontal we have just found, which is this one, so we are going to write it U of first. Then we know we have 0 displacement for node 2 in y direction, so simply 0, and then U 2 to 3. So this is the global displacement. Node 1 0 0, node 2 only horizontal, and node 3 horizontal and vertical. Now we can find the global force, which can be given by global stiffness matrix times U of G. So these are the reaction forces, which are horizontal and vertical reaction forces are 5 kilonewton and minus 1.25. So this is minus indicates the direction as downwards, and plus indicates the direction as upward, and similarly all other forces. Now let's find the stress, the last part. So for stress, we are going to define the displacement for each element. So for element 1, which is between 1 and 2, so we are going to have displacement as 1 2 and 3 4 at node 2. So UG of 1, UG of UG of 2, UG of 3, UG of 4. So this is the displacement for element 1 connected between node 1 and 2. Similarly, we can find the displacement for element 2 as, so element 2 is connected between 1 and 3, so UG of 1, UG of 2. Now this time for node 3 we are going to have UG of 5 and UG of 6, correct? And the last element, which is element 3, we are going to have the element between 2 and 3, which means 3, UG of 4, UG of 5, and the last UG of 6. So we have all the element displacements numbered as U1, U2 and U3. Now the last part, we are going to find the stress. We are going to find the stress in each element. For finding a stress, I'm going to use a little bit of for loop. So for element equals 1 and 1 equals same from here, can copy till sin theta. Okay, then we have formula for sigma 1 as E upon L cross minus C minus S, C and S times displacement of element 1, which is U1, and then end this. So you can give sigma 1 so we have the sigma 1 5.833, correct. So for finding the sigma for element 2 and 3, you are going simply, you do have to do nothing, but you have to do replace this element equals to 1. This time you will replace this one by element 2, and this U1 will be replaced by U2, and similarly for element 3. So I'm going to do it for you. Just a second. I'm just copying. I can just copy this one, Control C, Control V. This time 2, this time 2. Let's run it. Okay, here you also have to type 2. So element 2 is minus 1.5023, correct. And the last one is for element 3, sigma 3 and U3. So third element sigma will be minus 1.0516. So then you can type here as sigma 1, sigma 2, sigma 3. you'll get all your sigma values for each element. So let's describe how we can find the sigma for each element. So let's come forward. Okay, so what this for loop is doing is it's taking the element 1, it's finding the node 1, node 2, x1, y1, x2, y2 and theta, and then substituting all these values in over here, so which gives us the value of 5.833. So just a simple code, this one, so you can use it to find the plane, to solve the problems of plane truss elements in using MATLAB. So I hope you guys like this and subscribe to my channel for more videos like this, and we'll see you in another video very soon. Comment down if you have any doubts and like this video, subscribe to my channel. Thank you so much and peace.